And so the next talk in this session is a team talk, urban eddy covariance, why, how, and where. And this talk is being led by Kenneth Davis.
Hello. I'm going to try this screen share. Is this working?
Looks good.
Looks great.
Thank you. Great. All right. Thanks very much for having us. We're going to try to give you a lightning tour of the work that our group is doing on urban eddy covariance measurements. And we have a very diverse and early career team here. We've finally refined this presentation. Our handouts will be flawless, I'm sure. So I'm going to start out just to introduce the topic. I've worked for a long time, both in the flux world and in this world of urban greenhouse gas inversions. And the inversion studies, this is a map of sites, tower sites around 6 different cities in North America. These are all mole fraction measurements on communications towers. These are not flux towers. So the question is, and this is dominated by atmospheric inversion work. So why aren't we using flux towers? Do they have a role? And can they be used to complement what we learned from the inversion world? And my answers to that are good question. And yes, we are using flux towers. They do have a role, and we're going to demonstrate. First, I want to hit why. And I argue that the why for urban eddy covariance is the same as the why for ecosystem studies. These towers are great sources of process level understanding to test our models. They're complementary to inversions, which do large scale and get the whole system as a net. Urban systems are not too complex for these towers, and we're going to try to prove that to you. So we're going to go through there's 3 objectives we see. We're going to go through 2 of them, focused on the CO2. We need to understand the process level performance of anthropogenic models and of ecosystem models, both in and around the urban system. And we also, the point we're not going to go into today, which is still relevant, is these measurements can help us understand the momentum and energy fluxes that drive the boundary layer that we need to simulate the greenhouse gas budgets. So to that end, our group has deployed a bunch of urban and near urban, or we call it the rural surroundings, flux towers, mostly around Indianapolis, but we're expanding into the Northeast corridor. And we'll visit most of these towers over the course of the talk. We've kind of adopted Monroe Morgan State Forest, as long as that's okay with Kim. So first off, I want to go into the work to understand the process level functioning of a high resolution urban emissions, anthropogenic emissions model. Before I turn that over to Kai Wu, who is a postdoc now at University of Edinburgh, I want to say, well, wait a minute. Don't the atmospheric inversions do this? And again, I would say no. We often compare inversions to the bottom up on a whole system scale, but to understand the processes and how well they do at high space and time resolution, I think we want to go to flux towers. So with that, I'm going to turn it over to Kai. If I can advance the slide successfully. There we go. Whoops, I jumped ahead one. There you go, Kai. Sorry, it was just a big graphic.
No problem. Thanks, Ken. Yes, so here we measure net CO2 fluxes at Tower 2, which is located in a suburban area. And we also measure CO and CO2 mole fractions at this site at 10 meters and 40 meters height. At this site, we can see there is a highway to the north and the urban vegetation to the south, surrounded with detached houses. We use a flux footprint model to quantify the footprint of this flux data. Next slide, please. Yes, so here we check the temporal and spatial variations of these flux measurements. In your left hand, we can see the seasonally averaged diurnal variations of this flux measurement during the cold season and the warm season. In the cold season, which we define from January to March, there are 2 prominent emission peaks during the rush hours, which is related to the traffic emissions. And in the warm season, which we define from April to July, we can see a photosynthetic photosynthetic uptake during the afternoon, which is corresponding to the biogenic CO2 fluxes. The bottom right panels show the spatial patterns of this flux data. We can see high emissions from the north and the smaller or negative fluxes from the southwest of the tower, which is corresponding to the surrounding environment. Next slide, please. Okay,
Sorry.
so
There you go.
that's fine. Yeah. So these are the total CO2 flux measurements, but we cannot compare them with the Hestia directly. And then we did additional 2 steps. The first one, we decompose this flux data into biogenic and the fossil fuel components using CO measurements and flux gradient relation. And the second step, we match the Hestia emissions in space with a flux footprint model. And then we estimate the predicted Hestia emissions at the tower locations. Then we can do a apple-to-apple comparison. Okay, here is the results. The top 2 panels show the histogram of flux difference between the Hestia and the partitioned fossil fuel emissions in the cold season and the warm season. And we can see the bias is quite small. The bias in Hestia is quite small, and the bias percentage is 3% in the cold season and 9% in the warm season. If we further check the temporal variations, the seasonally averaged Hestia emission match quite well with the partitioned fossil fuel emissions after we do the seasonally averaged. So in general, we found the decomposed fossil fuel emissions match quite well with the Hestia. I will stop here.
All right,
Thanks.
and so just thank you very much, Kai. Just a quick capper. So that this is, to our knowledge, the first time this kind of a high resolution comparison has been done. And this is extremely encouraging. Hestia takes a lot of work to create, and the flux decomposition approach appears to work. We see this almost as much as a test of the decomposition approach as it is a test of Hestia. But we're very encouraged. So I'm going to next move on to an application of this approach to detection of an event, the COVID lockdown, and turn it over to Eli Vogel, who is a senior in physics at the University of Maryland, Baltimore County.
So the problem with inventory models is that they're not as good at monitoring specific events, but FlexTower should be better at that. To see if that's the case, we have Tower 7 shown by the star on the Google Maps image to the right. It's in the western part of Indianapolis. The red circle indicates the approximate footprint of the tower, about 400 meters in diameter. It was originally meant to monitor emissions from the urban forest to the west, but when COVID-19 resulted in an extended lockdown in Indianapolis in 2020, this was a good chance to see how the pandemic affected traffic emissions from Interstate 465 to the east. So in order to compare emissions before and during lockdown, we had to choose 2 analysis periods. To the left is a graph of Apple mobility data from 2020, showing the relative number of directions requests Apple users made each day compared to January 13th. We chose a pre-lockdown period of February 5th to March 3rd before Apple mobility drops. The lockdown period is the 4 weeks just after Indiana's statewide lockdown went into effect, indicated by the red asterisk. So Apple mobility data and data from the Indiana Department of Transportation suggests the lockdown period saw much less traffic in Indianapolis, including on I-465. And according to Tower 7, there are a lot less fossil fuel CO2 emissions as well. So the right is a graph of the hourly average of both periods, ignoring weekends, and only using measurements taken when wind was blowing from the east, and also using the method of disaggregation described previously. So the red corresponds to pre-lockdown, the blue corresponds to lockdown. The drop in average hourly emissions is pretty stark here, as you can see. Next slide.
There you go.
Yep. When you compare these pre-lockdown and lockdown analyses with hourly traffic counts from Indiana Department of Transportation of a highway close to I-465, there is correlation. So the disaggregation results are promising. There is worse correlation during lockdown, although that could be reflective of other emission sources becoming more prevalent during lockdown. So from the results, we can feel confident in the flex tower's ability to monitor emissions changes at smaller timescales and inventories, and the disaggregation method helps to ensure we're just looking at fossil fuel emissions. Combining inventory models with analyses of isolated events like this one would be very useful, and hopefully will be to monitor mitigation efforts rather than pandemic-induced lockdowns.
Cool. Thank you, Eli. Next, sorry, my transition has got a delay time here, but next I'm trying to show you the cool slide that says we're going to next watch the grass grow. And I'm going to turn it over to Claire Jin, who is in her first year as an undergraduate at Carnegie Mellon.
Yeah, so urban regions are not devoid of plants and other sources of biological fluxes. So in order to accurately extract anthropogenic emissions from overall emission measurements in an urban region, we need to be able to accurately model those biological fluxes. So to do this, next slide, we isolate the plants found in an urban environment and look at their emission patterns, or as we said, watch the grass grow. So specifically, we focused on 3 urban turf grass sites with varying levels of management to the grass. So 2 of the sites were located in Indianapolis, while the 3rd one, NIST, is in Maryland near the Capitol, using 3-meter tall flux towers with all the typical flux tower equipment. We collected measurements over turf grass fields in Indianapolis from 2017 to 2019 and at NIST starting in 2020. So, and this is great and all, we all love flex towers, but why the focus on turf grass? And the answer to that question is that turf grass is unexpectedly photosynthetically active in the winter. So as you can see on the left graph, in the winter, turf grass has a daytime CO2 fluxes shown in red of much greater magnitude than corn or soy, which are shown in blue and green. However, in the summer, as we can see on the right graph, the turf grass tends to be much less photosynthetically active than corn and soy. This may be because the turf grass in temperate climates is selected to stay green as it gets cooler and not grow super rapidly in the summer, but whatever the reason, this behavior was completely unexpected and unaccounted for. The previous assumption for the dormant season was that biological fluxes are insignificant. However, the daytime flux magnitude of urban turf grasses, or of their photosynthetic activity, is actually comparable to fossil fuel emissions, and that's pretty big. So it's really important that current ecosystem models be adapted to the turf grass flux pattern. So in order to do this, we needed to choose the biological flux model parameters in a data-driven way. So using the VPRM model structure, we optimized the parameters to best fit the flux tower data collected at the 3 turf grass sites I talked about before. So here we show the measured daytime fluxes in the red or pink color, the model with the new parameters for turf grass in green, and a model for grasses which are not turf grass in blue. And a major difference between these 2 parameter sets is the T-min parameter, which marks the air temperature under which biological fluxes can be set to 0. So for the non-turf grass, T-min was 2 degrees Celsius, while for the turf grass, it was negative 3.5 degrees Celsius. And as you can see, this change greatly improves the fit. The green, which is the new parameters, fits the measured data much better than the blue, which tends to underestimate the daytime flux. However, the optimization is still in progress, since neither model fully captures that springtime increase in flux magnitude around day 100, circled there in blue. But our current results look very promising. So yeah.
Thank you, Claire. And now next, I'll turn it over to Sam Murphy, who's in her first year and a little bit as a master's student at Penn State, and she's watching the corn grow. And first, wait a minute, this is corn. It's not urban ecosystems. Why?
So the figure on the left here helps illustrate why the background agricultural fluxes matter. And this figure shows the calculated CO2 enhancement using Tower 9 as a background. And what I really want to focus on here is the growing season difference between the observations at Tower 9 and 2 other potential background towers, 1 and 14, which are highlighted by the red box. And importantly, the differences between these 3 sites during the growing season are on the same order of magnitude as the urban enhancements themselves. And now Tower 9 is surrounded by agriculture, as is Tower 14, while Tower 1 is surrounded primarily by forest. Miles et al. 2021 suggests that the differences observed between Tower 9 and Tower 1 can be explained by the differences in land cover type surrounding the towers, while the mechanisms behind the differences in observations at the agricultural towers are still being explored. Next slide, please. And so we need to understand this rural background in order to understand the anthropogenic emissions. So let's discuss some ways we can do so. Thank you. And one way to do this and understand the rural background is through the use of eddy covariance flux towers. The figure on the left here shows that the flux towers in and around Indianapolis. Multiple flux towers have been deployed at corn and soybean fields in order to study the regional variations in agricultural fluxes. Corn productivity tends to vary from the east side to the west side of the city, as does corn and soy density, which could potentially contribute to this complex background conditions that we've observed. Next slide, please. And then currently we are using the vegetation photosynthesis respiration model that Claire mentioned earlier for an area of about 300 by 300 kilometers around Indianapolis for a period of about 10 years. And with these model runs, we can compare the model flux output to agricultural eddy covariance measurements like those I mentioned in the last slide. And that way we can determine if VPRM accurately represents the measurements. And if it doesn't, we can optimize the model parameters to better fit the data. We can also convolve the VPRM outputs with CO2 concentration tower influence functions. That way we can determine if VPRM is able to explain the background mole fraction differences that Miles et al. 2021 observed. And then both of these will ultimately help us move towards the goal of using VPRM to represent rural background conditions for urban inversions.
All right, thank you, Sam. That wraps up the presentation. I have a slide of conclusions, but I think I'll just leave it up there and stop because we're slightly over time. Thank you very much for your attention.